This is the second topic for the third chapter of the syllabus, which is the interference of light. In this particular presentation, we're going to be looking at a few definitions. This is actually a very big topic in the syllabus. These are the first 3 dot points from this topic. However, in this presentation, we're just going to cover the first one, and in order to do that, a few definitions are required. So when we look at an electromagnetic wave, we can draw it on the page like we've got here. This is maybe a typical sine wave or something. Now, when we talk about the electric field component, this is a field component that we draw on our diagram. And we must remember though, there's a magnetic component that is perpendicular to this going in and out of the page with a direction of travel of the wave, typically left to right as part of convention. Now I'd like to introduce the definition of phase. Now 2 wave sources are in phase if the wave that they produce has the same displacement and direction. So you can see from the diagram, whenever source 1 emits a crest, source 2 does it at the same time, and same with a trough as well. Now if 2 waves are not in phase, they're out of phase. This is when the crests don't line up or another part of the wave doesn't line up. Now you can see in the diagram on the right, there's a difference between the 2 waves. So this is called a phase shift. So when one source produces a crest, the other source produces another part of the wave. Now you can see on the diagram on the left here that in image 1 we've got a wave, and say we've got source 2 is producing the wave at the same time. This will be in phase. Now when we look at source 3, you can see that there's a difference between source 3 and source 1, and there's a phase shift of what we say 90 degrees here. And if we look at image 4 compared to image 1, there's a phase shift of 180 degrees, but we can also say this is half a wavelength out. Now I'd like to introduce the definition of coherence. Now 2 wave sources can be coherent if there's a constant relationship between the wave sources in terms of the waves they produce. So this means that the waves from both sources have to have the same frequency, speed and wavelength to maintain a constant relationship. So we can see in this first diagram here, these are actually in phase, and you can see there's a pink and a blue wave, and they're matching up. In the second diagram, there's 2 waves, a pink and a blue one. They're out of phase, but you can see there's a constant relationship there. There's a phase shift, but it's constant. So these waves are coherent. Now in the third diagram, these are completely out of phase, meaning there's 180 degrees phase shift, or the wavelengths are half a wavelength out. Now these are still coherent as there's a constant relationship there. Another definition is monochromatic light. Mono meaning single, and chromatic meaning color, so it's a light of a single frequency. I think we're up to our 5th definition now for this slide. So this is incandescent light. Now this is a light that's produced due to the application of heat. So for example, the filament in a light globe has electricity applied to it, it heats up that little filament. If it gets to a point that it's so hot, there's so much energy in the particles that it starts to glow. Now this glowing actually produces a light, obviously, and this is incandescent light. When heat is applied to a material, the energy that's associated with that is shared amongst the particles in the material. However, these particles are at different orientations and different locations within the material. So when the particles receive the energy, if they get enough energy, they emit a light or a photon of a certain wavelength. Now because of the randomness of this, it's neither monochromatic or coherent. Now you can see by this graph that I've got that there are, for the number of particles that are in the material, they might get a different amount of energy. However, if you can see here, maybe at this point, most of the particles, you might say, get a certain amount of energy, and the color that is associated with the glow is related to this energy level. Now if you apply more energy, the average color that you'll see will change. So this might be a red color here, but as you go further to the right, a little bit more energy, and you might move up the visual spectrum and you might see more of a yellow glow.